Let's continue with the topic of sound waves. Now, as you know, sound wave is a longitudinal wave. It's not the transverse wave we discussed before, right? When you compress or have a rarefaction or compression on the air column, the air molecule vibrates along the direction of travel of the waves, right? They vibrate along that direction. Okay, so that means the sound wave is a longitudinal wave. So let's just consider an air column. An air column, a short air column that extend from x to x plus delta x. Now, x is a label, just like a label on a string. It labels different position of the particle. Now it labels the air particle. The air particle, which are initially here, has a label x. And the air particle, which is initially at this position, has a position label of x plus delta x. Okay, so that is a label for different for particle at different position in the air column. Okay, but now the air particle will be displaced either to the right or to the left, right? About that equilibrium position. This is an equilibrium position. This x is the particle at rest is here. But now, and as a sound wave pass, the air particle may be displaced to the left, to the right, or to the left. Okay, and we denote in our convention is that the wave is traveling to the right. So our convention is that the displacement to the right is taken as positive, and that to the left is taken as negative. And we denote this displacement by u. Okay, so u is again a function of x and t. Different position, the particle at different position will have different displacement, and the displacement also depends on time when the wave passes. Okay, so initially the particle is here, but now at a certain time, the particle has displaced to this new position, and the length here, the red arrow, the length of the red arrow is u at xt. And similarly, at this position x plus delta x, the particle at time t is displaced to here. So the length of the displacement is u x plus delta x, comma t. Okay. So the two particles have different displacement, right? Because they are at different position of the wave, so you naturally expect they have different displacement relative to each other. If the two particles have the same displacement, the whole column of air will be just shifting to the right without expanding or compressing. If they have the same displacement, then the column of air is still maintain its length, right? It will not be compressed or rarefacted. But if one end is displaced at a larger amount than the other end, then the length of the air column will change. Is that right? And so how do we calculate the change in that air column? The change in that air column can be found by the difference in u plus x plus delta x minus u. If the 2u at the two ends are the same, that corresponding only to a shifting of the column as a whole without any change in size, then the change in volume will be 0. But if one end changed by a larger amount than the other end, the difference will give rise to change in the volume of the column. Okay. So now we denote the initial volume as delta x, which is the difference between these two ends, right? This is the length of the column, original length of the column, multiplied by the cross-sectional area A. And we denote the change in volume when the wave passes by V1. How do we find V1? Well, V1 is the difference in u on the both ends, u at x plus delta x minus u at x, multiplied by the cross-sectional area. Okay, so when the two u are the same, V1 is 0. There's no change in volume. When u at x plus delta x is larger than u at x, then the air column will expand. Right? If U at x plus delta x is more than Ux, then the column will contract. Okay, so that's how you find the change in volume. Okay, but obviously this is the function you vary at x plus delta x minus the function you vary at x. So naturally, we can do the same before. We can express it as the derivative, the spatial derivative multiplied by delta x. Now, because if you notice that a function you vary at x plus delta x minus a function you vary at x divided by delta x is almost equal to its derivative, right? If delta x tends to 0, that is exactly the derivative, the definition of the derivative, right? So you can imagine now, if I have delta x sufficiently small, I can write the difference x plus delta x minus fx approximately as the derivative at x multiplied by delta x. And that is exactly the approximation we have made. We replace the difference of the u between two ends by the derivative of u multiplied by delta x. This is a spatial derivative of u. So I have round u round x, okay? Because u depends on x and t, so I use a partial derivative. Okay, so I differentiate with respect to x and then multiply by delta x, which is this guy. Okay. But delta x multiplied by a is just the original volume. So this is V naught. Okay. So the result is very simple. The result is that the change in volume V1 over the original volume. The change in volume over the original volume is equal to du dx, round u round x, right? Now the change in volume will give rise to a change in pressure, because when the air column is compressed or extended, there should be a corresponding change in pressure, which we call P1. Now the equilibrium pressure we denote that by P naught. P naught is a simple atmospheric pressure. But if I have a disturbance now, if the wave passes, there will be a change in pressure. And we denote that part of change, that changing part, by this function, P1 as a function of x and time t. If there's no disturbance, if there's no u, then the P is 0, the P1 is 0. We only have the atmospheric pressure at equilibrium. But when you have a different, the particle are moving, the air molecule are moving, you have different u at different position, then there will be a change in volume of the air column. You have V1, then you have a change in pressure V1. Okay. Now we postulate that we are not. We will show you later why this is true. We postulate that the change in pressure is proportional to the fractional change in volume. Now the change in volume divided by original volume is the fractional change, right? We assume that. We will prove it later, actually. We assume that the change in pressure, the resultant change in pressure due to the change in volume is proportional to the fractional change in volume. And the proportional constant, we called it the bulk modulus. The bulk modulus. The bulk modulus is a constant for a certain material. The negative sign denotes that the change in volume and the pressure are of opposite sign. If, for example, the volume has increased, that means a rarefaction, right? The volume increased, that means a rarefaction. The pressure will decrease, right? So P1 become negative when V1 is positive. When volume expand, positive V1, that result in a decrease in pressure. So P1 is negative. On the other hand, is P1, if V1 decrease, if V1 negative, if the volume decrease, if V1 is negative, then that means a compression. The compression will cause the P1, the pressure, to increase. Okay, so P1 will be positive. So that means that's why P1 and V1, they are opposite sign. Why do we have that's why we have a negative sign here. Okay, and they are proportional to each other. Okay, Now, what is the meaning of that bulk modulus? The bulk modulus is somehow the resistance to compression. Okay. Imagine now B is very large. VB takes on a very large value. So that means a small compression, a small change in volume will give you a large pressure change. And that means the object is very difficult to compress. You need a large pressure to make it change, to make its volume change by a little bit. So that means the object is very difficult to compress. So a larger value of B means the medium is more difficult to compress. It's difficult to compress. You need a large pressure to produce just a little bit change in volume. Okay. And a small b corresponding to an easily compressible medium. You only need a small force to not small pressure change to compress to make the volume to change by a large amount. Okay. Now, but we can express everything in terms of U. Because we know that V1 over V0 is round U round X, we have proven it before. So the pressure change, the P1 is just minus B round U round X. So this is the pressure force, the pressure change, P1. Now, what this equation says is that we relate the pressure change with the derivative, the spatial derivative of the displacement of the air molecule. Okay. Now we consider the force. We consider the force in this air column that extends from X to X plus delta X. Now, what is the net force acting on it? It's due to the pressure. The pressure on the two sides. Now, the equilibrium pressure must cancel each other, right? Because these two sides must have the same atmospheric pressure. That part will not change. So we don't consider that part because that part are always equal and they always cancel each other. What we want to consider is the pressure change. The pressure change at the side X may not be equal to the pressure change at the side X plus delta X. So the two pressure change are different. And if one side pressure change is larger than the other side, that will give rise to a net force. Okay, and the net force will cause the air column to accelerate. Is that right? So we want to find the pressure difference between the two sides. For this side, we have P1 X plus delta X, minus sign because it's exerting the pressure on the column to the negative X direction, right? So we have negative sign. And the other side, we have the pressure P1X, which is exerting the force to the positive side. So we have a plus sign here. The difference between the two, these are difference in pressure. The difference in pressure multiplied by the area is the difference of the force. It's the net force. Okay, so this term is just a net force acting on the air column by the surrounding pressure. Okay, the surrounding pressure change exert a force equal to this on the air column. Okay. Now you can immediately see that if I extract a minus sign out, then P1 X plus delta X minus P1 X is round P1 round X, right? Multiplied by delta X. We have the same trick as before. In the previous slide, we used this relation, right, to approximate U, the difference in U by round U round X delta X, right? Now we can apply the same for P. Okay, if this function stands for P, we have P X plus delta X minus Px divided by delta X, and that is the derivative of P, right? So we can also move the delta X to the right-hand side to find the difference, right? So the difference between the two P is round P round X, round P1 round X multiplied by delta X. Okay. But as we know, P1 itself is minus B round U round X, which is already the derivative of U with respect to X. So now I have one more derivative because I differentiate P1. So I got a second derivative and the two negative signs in the equation cancel. So I got the second derivative of U with respect to X multiplied by B, the bulk modulus, multiplied by delta X, multiplied by A. It is the net force. So we can now apply Newton's second law now, right? Newton's second law say that the net force acting on the air column is equal to the mass of the air column multiplied by its acceleration. So what is the mass of the air column? Well, the equilibrium length of the air column is delta x, the length is delta x, multiplied by A is the volume. The volume multiplied by the density, the equilibrium density, which we denote by rho naught. Rho naught is the density without wave, the waves. It is the equilibrium density, right? So the equilibrium density multiplied by the volume, equilibrium volume, is the mass of air there. Okay. And the acceleration is given by round square u round t square. It is simply the second derivative of u with respect to time. It is the acceleration of the whole column. Okay, so it is simple application of Newton's second law, but to a continuous medium. Okay, we equate the pressure difference, the force produced by pressure difference, with the mass times the acceleration of the air column. Okay. Now you immediately see that the delta x cancel, the A also cancel on both sides, and that result in a familiar wave equation. Okay, we have the spatial derivative, the second spatial derivative of x equal to the second temporal derivative of u with respect to time, right? And the constant in between is rho naught over b. Okay. Now, but this takes the form of a general wave equation. In a general, when we derive the wave equation for the string, for vibrating string, the transverse wave on the vibrating string, we have arrived at this equation. And in that case, v square is equal to tau over mu, right? We have the constant, actually we have the constant mu over tau here. So v square is tau over mu. V is square root of tau over mu. Now we have another constant that involves the bulk modulus and the equilibrium density. So if I write this equation like this, I can identify the velocity. That is the velocity of the sound wave. The velocity of a sound wave is the b divided by rho naught, because v squared is b over rho naught. So v is just square root of b over rho naught. Okay, it is a square root of the bulk modulus divided by the equilibrium density. And because this is a wave equation that we have solved, we don't have to solve it again. We simply state that the traveling wave solution is a solution to that problem. We simply say that the traveling wave solution is u naught cosine kx plus minus omega t or plus omega t. Okay, but omega and k are not arbitrary. They are constrained by the medium. Now omega over k must be equal to the wave speed in order for this equation, this solution, to satisfy the wave equation, right? Omega over k must be equal to v, and v is determined by the properties of the medium, which is the bulk modulus, and the density. Okay. Now we can find the pressure change from the displacement. We now know the displacement u, and the previous discussion tells me that if I differentiate u and add a constant minus the bulk modulus, I got a pressure change. So we have a straightforward differentiation of this. Differentiate cosine give me a minus sign. Okay, and differentiation by chain rule, we have a factor of k pulling out. Okay, the minus sign of the derivative cancel with this minus sign, so we have a plus here. Okay, so that the pressure change become a constant u naught bk multiplied by sine kx omega minus omega t. Now we may also write the pressure change in a nicer form. In a previous formula, we express it in terms of b and k. But we can also express it in terms of the speed, because we know that v squared is b over rho naught. So we can rewrite B as rho naught V squared. Okay. And we also know that V is equal to omega of K. So we can write K as omega over V. And this equation allowed me to cancel one of the V. And so the amplitude for the pressure change will become rho naught V omega U naught. Now this equation has the advantage of expressing the amplitude in terms of the velocity. Okay, this is the displacement amplitude is always there. The U naught is always there, but we have the advantage that to express the pressure change in terms of the V, in terms of the wave speed of sound. Okay, in the medium, which we may know by experiment. Okay. Now, because the pressure wave also depends in space and time with space and time as sine kx minus omega t, just like the displacement wave. Okay, they are the same form, except one goes as a cosine and the other one goes as a sine, but they take the same form. You can see this is a traveling wave with this amplitude. So that means the pressure wave also will satisfy the wave equation. Okay, because omega and k they are related, just related as the same way as the displacement. So because of this, we claim that the pressure waves also satisfy the same wave equation as the displacement waves. Okay, but when you examine the two solutions, when you examine the U and you examine the P1, you find that they have a relative phase shift of pi over 2. Because the disturbance, the displacement wave goes at the cosine. Take a snapshot. Suppose we look at the wave at time 0. Suppose we look at the wave at t equal to 0. So we don't have this term. So the displacement wave goes as cosine kx at time 0. And the pressure wave P1 goes as a sine. The sine function is something like this, right? Now the cosine function is this, the sine function is this. So the displacement and the pressure, they have a relative phase shift. The phase shift is a quarter of a period. If you shift the displacement curve to the right by a quarter of a period, you get a pressure wave form. Okay, of course the amplitude are different, but they have the phase shifting relative to each other by pi over 2. Okay, and you can now also see that the maximum of U correspond to a 0 in P, and the 0 on U corresponding to a maximum in P. Okay, that's or minimum 0 in U here correspond to a maximum or minimum in P. Okay, so that is a very interesting features. So they are always out of phase by pi over 2. Okay, a quarter of a period. So one goes to maximum, the other one will go to 0, and vice versa. Okay. Now, you may have difficulty understanding this very abstract derivation. Why? You may ask why the displacement and the pressure change they have a phase shift of pi over 2. You may wonder why. Now look at this figure. This figure helps you to understand why this is so. Now this is the curve of U at time 0. Okay, it's a cosine curve. This is the curve of the pressure wave P1, also at time 0, and that is a sine curve. Now look at this position. This position has what? Has the largest pressure, right? It's the largest pressure. So that means it's what? How do we say that for waves? A largest pressure region is a compression region. The compression region has the largest pressure. So that means the density here has increased, right? The particle is becoming, getting more closer together at this position. and that means a compression. Okay, so more particle is concentrating here. Okay, but where do the particle come from? It comes from either from the left or to the right, right? You can see from at x equal to 0 here, the disturbance is maximum, is positive maximum. So it means that the particle here, it goes to the right because a positive value means going to the right. So the particle at x equal to 0, they go to the right side by a larger displacement. So the particle here will go to this side by a largest displacement. Now, similarly, if we look at this position, this is the position with a minimum u, with a largest negative value of u. So this position, the particle in this position have a displacement in the negative x direction with a maximum amplitude. So the particle here will move to the left by the maximum amount. So what happens is that this becomes a compression in the middle. The particle here move to the right, and the particle here move to the left, right? So the two side is compressing the middle one, right? So that the here become a compression, which is exactly representing by the maximum value of P1. And similarly, if you look at this position, which is a rarefaction. Now this position has a lowest pressure, right? P1 is smallest, right? So it has a lowest pressure. Why there's a lowest pressure here? Because the particle here goes away, on the two sides goes away. On this side, the particle goes to the left, leaving this region. And on this side, the particle go to the right. So the particle separate. Instead of compressing, it separates from each other. So here, it becomes a rarefaction. Okay, so the pressure change here, maximum, minimum, maximum, minimum, it corresponds to a compression, rarefaction, compression, rarefaction. Okay, and the compression and rarefaction are due to the motion, due to the displacement of the adjacent molecule. If the adjacent molecule are on the two sides are pressing together, that become a compression. If the molecules on the two sides are separating together, separating from each other, that become a rarefaction. Okay, so you now understand why U and P1 are of the opposite phase, or has a phase shift of power 2. Okay. Haven't derived such a interesting, beautiful wave equation for the sound wave. Now you can see that the sound wave equation is exactly the same as almost exactly the same as the transverse wave on the string, right? They are of the same form actually. The only difference is the wave speed. For the string, we express the wave speed in terms of the tangent tau and the density of the string. Now for the sound wave, the same equation result. But the wave speed, it depends on the bulk, so-called bulk modulus and the density of air, right? So that is the difference. But the equation has the same form. In fact, all linear wave motion follow the same wave equation. The velocity for different medium, it only depends on the physical property of different medium. That is the only difference. As long as you have the linear wave propagating in a medium, you always can have the same wave equation to describe the motion. Okay. Now, but we have been using the so-called bulk modulus for many steps, right? So what hell is the bulk modulus? Okay, what is actually a step? Now, the simplest approximation by Newton in 300 years ago, he assumed that when the air is get compressed or rarefied, okay, when the air is compressed or rarefied, the changes happen at constant temperature. So the temperature doesn't change. We assume that when it's compressed or rarefied, the air still remains the same temperature. And if the simplest approximation to a gas, at constant temperature is the so-called ideal gas law. I can apply the ideal gas law, BV equal to nRT, the equation you have learned, and I set T equal to constant. All right, that is the simplest approximation I can think of. Of course, a real gas may not follow this ideal gas equation, but that is the simplest model we are available. Okay, so let's assume ideal gas law hold, and the temperature is a constant, and see what will then be the Bragg modulus. Now, if PV is equal to a constant, then I differentiate the left-hand side. The right-hand side is 0 because the right-hand side is a constant. So when I differentiate the differentiation constant, that becomes 0. So it doesn't change. So by the product rule, when I differentiate PV, it becomes VdP plus PdV, right? A simple application of the chain rule, product rule. Okay. Now let's make an approximation now. dP and dV correspond to infinitely small change, but now we make it finite. When we make it finite, that is not strictly correct. It's approximation only. So we replace the equal sign by the approximation sign. The change in P corresponding to the pressure waves, that is P1. This is a change in pressure, right? The change in V, dV corresponding to what? Corresponding to V1, the change in volume of the air column. The original volume is V0. The original pressure is P0. Okay, so the equation now becomes V0 plus V0 P1 plus P0 V1. And the two times add up to 0. So we can solve for P1. So P1 will then be equal to minus P0 multiplied by V1 over V0. Now you immediately realize that this equation take the same form as our previous equation, our previous assumption. Our previous assumption is this. We assume P1 to be equal to minus B V1 over V0. So we now can identify what is B. B is simply what? B is simply the atmospheric pressure, P0. Okay, the equilibrium pressure, not necessarily atmospheric pressure, but the equilibrium pressure of the gas. Okay, so that means what? That means with B equal to P0, the wave speed, the speed of sound in air is just square root P0 over V0, over rho naught. Now this is exactly what Newton got I think 300 something years ago. When Newton first derived the speed of sound, he got this equation. Okay, but unfortunately, this is wrong. Newton's was wrong in this part. Why? Why was he wrong? Now it turns out that when air is compressed by the pressure wave, it has a temperature change. Imagine you have a bottle of gas and you compress it with a large force, just like you pump air into the tide, for example. You dust work on it, right? When you dust work, you input energy to the gas and the gas gets heat up, right? So when there's a compression, the gas that does get heats up, the temperature increase. And when there's a rarefaction, when the air density decreases, the air pressure, the gas does work in doing the expansion, and there's energy loss, and so the temperature will decrease. So there's in fact a temperature change when the sound wave passes the air. When there's a compression, the temperature increase. When there's a rarefaction, the temperature decreases slightly. Now, but the compression and rarefaction, they last for a very short time. The sound wave is passing the air very quickly. So all the changes happen very rapidly. And if the change is happening very rapidly, there's no time for the gas to exchange heat with the surrounding. Now, when hot object is contact with a cold object, then the heat will flow from the hot object to the cold object. But that takes time, right? You have to make the two objects in contact for a certain time for substantial heat to flow from the hot object to the cold object. But if the compression and rarefaction are happening so fast, it happened in the blink of an eye, the air that gets compressed or rarefacted, it does not have any time to exchange heat with the surrounding air. So that means the process is happening so-called adiabatically. It's a so-called adiabatic process. Adiabatic means no heat exchange. It makes the gas compressed or rarefacted without exchanging heat with the surrounding. And a gas under adiabatic compression will satisfy the following equation of state. Instead of just writing PV equal to constant, now PV equal to constant corresponding to a constant temperature. If I assume an ideal gas and I assume that PV is a constant, that means the temperature T is a constant. That is a necessary consequence if I apply the ideal gas law with P equal to constant, right? That is Boyle's law, right? But now you notice that this equation of state is different. It's not PV equal to constant, but PV raised to a certain power. That power is gamma, which is a constant. The constant is called adiabatic index. The name doesn't matter. The equation is PV raised to gamma equal to constant. And obviously, for this equation of state, it does not maintain the temperature T to be constant, because the ideal gas law still hold. So instead of PV equal to constant, we have PV gamma equal to constant. The temperature must change, right? And that is exactly the process which we call adiabatic process. The temperature will change when we compress or rarefact the gas. Yeah. Now, I haven't shown you how to derive this formula for the adiabatic process. But if you study physics for the second year, when I teach you thermodynamics in the first term, you will find that the constant gamma is a constant of unity, of the order of unity. And it depends on the degree of freedom of the air molecules. Okay, and for diatomic molecules means a molecule makes up of two atoms. Like for example, in air, we have the oxygen molecule make up of two oxygen atoms, nitrogen molecule make up of two nitrogen atoms. So those are the diatomic molecule. Molecule makes up of two atoms joining together. For a diatomic molecule, the degree of freedom, the molecule can move in 3 dimensions and it can rotate. And because of that, we find that the value of gamma is equal to about 1.4. Okay, don't worry if you don't know why. I haven't derived it for you. Okay, you will learn it in thermophysics if you proceed to study physics. Okay. Now, if I follow this equation instead of PV equal to constant, now I follow PV gamma equal to constant, and then I do the same direction as before. Okay, I just do the same derivative, differentiating this. Okay, and I find P1. I find that P1 will be equal to minus B, V naught over B, V1 over V naught, and I can identify my B. And I will find that the B, the bulk modulus, is gamma P naught, which is larger than the atmospheric pressure, because gamma is larger than 1. So eventually, if I take B equal to gamma B naught, then the velocity of sound will be square root of gamma P naught over rho naught, which is larger than this value. Okay. Now, here is the example. If we take gamma equal to 1.4 for air, because air is diatomic, the density of air at sea level is 1.2 kilogram per meter cube. And the pressure and standard atmospheric pressure of air is 1.01, 10 to the power 5 Pascal. If we put all this value into the equation, then we get a speed of sound as 343 meter per second, which is exactly the value. Okay, this value is correct, right? The velocity of sound actually depends on temperature. temperature will affect the density of the pressure of air. So it actually depends on temperature. But at normal temperature, at room temperature, at sea level, this is about the value. Okay. Now here we have a classwork. I better not talking too much here. Let's finish with this. Now here we have a classwork. The maximum sound pressure amplitude that the human ear can tolerate is about 28 Pascal. Now this is a very small value. Imagine there's a small change in pressure. The pressure change is as small as 28 Pascal, which is much smaller than the atmospheric pressure, which is of the order of 10 to the power 5, right? But that small change in pressure is already enough to produce a very loud sound that makes you barely tolerate. Okay, you feel very difficult to tolerate. If you have still a larger value for the pressure change, then you may damage your hearing. Okay. So even a small pressure change will cause a large loud sound, okay? And you are required to estimate the displacement amplitude of the air molecule. And we assume for simplicity, the frequency of the sound, this is a linear frequency, is 1000 hertz. The speed of sound is 434 meter per second, and density of air is 1.2 kilogram per meter cube. Now, so with this value, you can actually find because you know the pressure changed has an amplitude of 28 Pascal. So you can substitute 28 Pascal equal to this bunch of constant. Okay, you know, the density rho naught you know. Omega is different from f by omega equal to 2 pi f. Okay, so from this value you can find the amplitude for the displacement. And after doing all this substitution, you do it at home, you will find that the U naught is 1.1 times 10 to the power minus 5, which is very small. 10 to the power minus 3 is already a millimeter. So this is 100 of a millimeter. Okay, so when the sound passes, when very loud sound passes in air, the air molecule only vibrates with a 100 of a millimeter in amplitude, and that vibration, that's very small vibration, is enough to produce a very loud sound, which almost damage your hearing. Okay, that is the maximum sound the human ear can tolerate. Okay, so that is an interesting thing. Very small pressure change and very small disturbance already produce a large result in our hearing. Okay, so let's stop here.